Hi, and welcome to the Unit 2.1D Solutions Chemistry video. This video is broken down into two parts plus a supplemental. In part one, we're going to focus on the first half of key question two. All right, before we begin, we're going to do a quick recap of what we covered in Unit 2.1C and preview what we're going to cover in this unit. So in 2.1C, we looked at quantifying concentrations of species that fully dissolve. And here I would annotate when we say fully dissolve, we're talking about strong acids, strong bases, and soluble salts. The techniques that we used were mole map and stoichiometry, which you can use to quantify the concentrations of your solutions. And we also learned a shortcut, which the M1V1 equals M2V2, which you can use when you are diluting something. So you're making a solution more dilute, or you're making a solution more concentrated as well. And so I would sort of annotate that here. This is used for dilutions or making solutions more concentrated. In this video, we're going to learn how to quantify concentrations of things that do not fully dissolve. So the difference is for 2.1C, it was things that do fully dissolve, and here is things that do not fully dissolve. And that would include, of course, weak acids, weak bases, and insoluble salts. All right, so let's compare the two. If we were asked a question like what concentration of Cl- are in a solution made from, let's say, sodium chloride, 1 gram of it dissolved in 18 milliliters of water. So sodium chloride is a soluble salt, so if you dissolve it in water, all of it's going to break apart into its ions. And so that's easy enough to do. We could use our mapping strategy here. We would start with 1 gram of sodium chloride, use that to figure out the moles of sodium chloride. From the moles of sodium chloride, we can figure out the moles of chloride ions, and we would do this conversion using the coefficients in the balanced chemical equation as our conversion factor. And once we have the moles of chloride, we would figure out the molarity. And I just want to note here that this symbol, this bracket, is the symbol for concentration. So we're going to start getting used to seeing this instead of seeing molarity or concentration, but they mean the same thing. There's just one symbol for it. So this is the concentration of chloride. Okay, so we can do that for sodium chloride, and that's because when you dissolve sodium chloride in water, all of it is going to break apart into its ions. So that means that the molar ratio, if you have 1 mole of sodium chloride, you expect that you're going to get 1 mole of chloride ion. But what happens if you have something like silver chloride? So we're going to do the same thing. So what are the concentration of chloride ions in a solution made from 1 gram of silver chloride and 18 milliliters of water? You may remember that silver chloride does not fully dissolve, and we indicate that here with these double arrows. So if you start off with 1 mole of silver chloride and you try to put that in water to dissolve it, you don't know how much of it is actually going to break apart into chloride ions, because some of it will and some of it will stay as silver chloride. Okay, so we cannot use mole map and stoichiometry here, and that's because not all of the silver chloride completely ionizes. So what do we use in that case? What we're going to use is what's known as the equilibrium constant, and what the equilibrium constant does is it tells us the degree of ionization, and the greater the K, the more favorable the forward reaction, meaning the more it ionizes. K is used for all sorts of things, by the way. It basically tells us how much the forward reaction, or how much the reaction goes in the forward direction. K's have the equilibrium constant, which are given the symbol K. They have a numerical value and an expression. We'll take a look at how we write the expression using this balanced equation. So in this balanced equation, capital A and capital B are our reactants, and lowercase a and lowercase b are the coefficients for the reactants. Capital D and E are our products, and lowercase d and lowercase e are our coefficients. So for the equilibrium expression, it's products over reactants. So we write K, and it's going to be divided by the concentrations of our products raised to the power of their coefficients. So you can see that here, concentration of D raised to the power of its coefficient, multiplied by the concentration of E raised by the power of its coefficient, divided by the concentration of reactant A raised to the power of its coefficient, and the concentration of reactant B raised to the power of its coefficient. All right, so key things to know is that K is products over reactants, and the more products you have, the greater the K. So because products are on top. If you have more products, that's going to increase the K value. Last quick note, we do not put solids or liquids into the expression for K. So gases are all right. You can put gases in here. You can put aqueous solutions, but solids or liquids would not go in here. In fact, if you have a solid or liquid, you can convert that into a 1 or just leave it out. All right, so I just want to quickly note that there are different types of Ks. We're going to be focusing on Ks where we're using concentrations, but you'll see in a later unit that you can also measure the amounts of things in pressure as well. But we're focusing on concentration because this is solutions chemistry. And there are also different types of Ks depending on the system. So Ka and Kb represent the ionization of an acid or a base, respectively. And the higher the Ka, the stronger the acid, and the higher the Kb, the stronger the base. So you want to definitely annotate that. So if you're comparing two acids or two bases and you have their Kas, you can tell by the Kas which one is stronger, and the same thing with the Kbs. Kw is the K for the ionization of water. It's given the value, it has a value 1.0 times 10 to the minus 14. You ought to memorize this. And so this is the number that you want to write down. So when you see Kw, you should know that at 25 degrees Celsius, it's equal to 1.0 times 10 to the minus 14. And the last K is for the ionization of a salt. So when you ionize a salt, this is the K that corresponds to it. It also typically follows the higher the KSP, the more soluble the salt. But it's important to note that it also depends on the ionization products, which we'll sort of see when we get to the supplemental section, but we won't really talk about that much here. All right, the best way to sort of get used to Ks or actually to do some problems, and you're going to be asked to write the KSP expression for barium chloride. So how do we tackle this? What we need to do first is we need to write out the balanced chemical equation for the ionization of the salt. So because it's a salt, barium chloride starts as a solid. Ionic compounds, we write them as solids, and that breaks apart into two ions, barium ion and then two chloride ions. Now for our KSP, it's going to be the concentration of the products over the reactants. But remember, this reactant is a solid, so we're not going to include it in the expression. If it was aqueous, we would, but since it's a solid, we do not. So it's just the products here. And notice that it's the concentration of barium times the concentration of chloride raised to the second power, and that second power comes from the coefficient in front of chloride. Since the coefficient in front of barium is 1, we don't have to write the power in there. Okay, so in this CFU, you're going to be asked, what is the KSP equation for the least soluble silver salt in the table below? So the first thing you need to do is pick the least soluble silver salt, and you want to do that by comparing the KSP values for each salt. And then once you do that, you're going to write the KSP equation similar to what you've seen before. Pause the video now. When you press play again, the answer will be revealed. Okay, so the least soluble salt is silver phosphate, and that's because it has the smallest KSP. So the smaller the KSP, the less soluble the salt. Again, we do need to worry about the ionization product, but in this case, because the numbers are so vastly different, we can easily look at this and just see it's the smallest KSP value to give us the least soluble salt. Once we know what salt we're looking at, we go ahead and write its ionization equation. So when we break silver phosphate down into its ions, this is what we get. And then the KSP expression is going to be the concentration of silver raised to the third power and concentration of phosphate raised to the power of 1, or we can leave the invisible 1 there. And again, remember the powers all come from the coefficients. Notice again, we do not include the salt here because it's in the solid phase. And this sort of points out why it's important to know what phases things are in, because when you write your equilibrium expression, you need to know if you should include it or leave it out. Okay, so let's look at Kas and Kbs now. Let's start with Ka. So Ka is for the ionization of a acid, and here we have a weak acid, sulfurous acid, H2SO3. And when you dissolve it in water, remember it's polyprotic, so we break it apart 1 proton at a time. So this is the equation we get when we remove 1 proton from it. All right, so what does the Ka look like? In this case, you know the reactant's in the aqueous, so we are going to include it in our K. And it's always concentration of products over reactants. So here we have concentration of H plus times concentration of HSO3. So that's what we have here. That's our products. And then over our reactants, concentration of H2SO3. And again, the reason why we include the reactant here is because it's aqueous, whereas for KSP, the reactants are solid, so we don't include them. All right, let's look for KB. Let's do it for NH3. So in this case, here we have this expression here, and there's a mistake here. That should be NH. The 4 should be a subscript, not a superscript. So please make that correction, make that 4 a subscript. But it results in NH4 plus and then OH minus. And for our KB expression, it's going to again be products over reactants. So this is what it would look like. These are our products. Each of these have a coefficient of 1, so the power here will be 1. And then the reactants, and NH3 would go in the bottom. Why don't we put H2O in our equilibrium expression? That's right, because remember, we do not include liquids or solids in the equilibrium expression, so they convert to a 1, or you can just leave them out. All right, last one is for Kw, equilibrium constant for water. So the equilibrium constant for the autoionization of water. What is that? The autoionization of water is when in water, it actually ionizes itself. So one water will act as an acid, one water will act as a base, and they one will give away its proton and one will accept the proton. And the product we get here is H3O plus, which is known as hydronium, and OH minus. So basically this is a double exchange reaction. And when we write it's Kw, since the reactants are liquids, we don't include them in the equilibrium expression. We just have our products, H3O plus and OH minus. And remember, this is equal to 1.0 times 10 to the minus 14. Again, this is something you ought to memorize. This expression will be useful later, but for right now, you just got to know what it looks like and how to write it. All right, here's our CFU for the CFU2. You're going to write K for the equation for the strongest acid in the table below. So just like in the previous CFU, you're going to compare their Ka's to figure out which one's the strongest. Once you know which one's the strongest, you're going to write the Ka expression for it. Pause the video now. When you press play again, the answer will be revealed. Okay, so this one is our strongest acid, and we know that because it has the highest Ka value. And this is the ionization of the acid, and there's a mistake here. Let me pause that now. Okay, so sorry about that, but I'm actually glad that mistake was made so we can sort of see it. So once again, we picked the strongest acid, which has the smallest Ka. And remember, for polyprotic acids, we break them down, we ionize them 1 proton at a time. So this would be the ionization of H3PO4. It breaks down to H plus and H2PO4 minus. Now, for our K expression, it's going to be the products over the reactants, their concentrations. And so we just go ahead and plug those in to the expression. Alrighty, so sort of to recap, you looked at how to write K equilibrium expressions. We're going to continue on with that vein in part 2. So this video is going to stop, and then we're going to go on to part 2.